So, yes. To get the centroid now for the whole built-up member or the component, you have to get the individual area and the centroid. Now, for the plate, the area is 1.5 inch square, no? And half of the thickness is the centroid of the plate, diba? For the wide flange, the area of this, if you try to look at in the table ASC, is 19.1 inches square, no? And the centroid is half of the depth. This is like 18 something, no? Half of that is 9.575. Then you multiply AW. I mean AY, A times this centroid, no, of each member. Then you add the area as well as this, the A times Y. With the addition of the cover plate, the shape is slightly unsymmetrical, but the flexural torsional effect will be negligible. Because of this plate, no? You added the plate. Nihimo siyang unsymmetrical. No, but because of this addition of plate, no, result is the flexural torsional effects is negligible na, no? So, dili na ni siya ma-account, no? The vertical axis of symmetry is one of the principal axis and its location need not be computed. So, for the vertical axis of symmetry, this one, actually, pwede dili na siya i-compute because if try to look at this member or this cross-section, the centroid, no, in the vertical axis of symmetry is just half. I mean, dili yun sa tunga because this is symmetrical man. But the horizontal principal axis will be found by the application of principle of moments. The sum of moments of component areas about any axis, in this example, a horizontal axis along the top of the plate, will be used must equal the moment of the total area. We use table 4.2 to keep track of the computation. Yes, to get this y bar, this is actually the centroid of the whole built up member of the whole component. So, I remember we get the summation of the value of a times y and the summation of the area so that the centroid for the whole component is the summation of this ay divided by the a. I don't know if you already tackled this one in statics or in the strength of materials, but this is actually a topic, no, in the strength of materials. I mean, included in the, as far as I remember, included in the example in the strength of materials. So, how to get the centroid of the different member, no? So, in ani siya pagkuha. You sum up, you get the area of each component, then you multiply, then sum up that one divided by the summation of the area. So that the centroid is equal to 8.893. Diba? This is just the centroid. So, kung 8.89 okay. This is, yes. Alright. Balik na dili sa kuan. Kinsa niya pagkuha ang kaning y. The reference of this one is this here. reference line. Okay, the reference line. So, ang centroid sa plate is from this line. Kung ano siya, dikit ni siya. From this line to this centroid. Diba? This line to the centroid is half, diba? Half of 3/8. So, that is, may mag-include the calculator. Ano ba ito diri? Calculator. Calculate. Okay. So, half of wala na. Half of 3/8. 3 divided by 3/8. Okay. Divided by 2, diba? That is 0.1875, diba? So, muna siya. Then, this is for a plate. For the white flange is from this reference to the centroid of the white flange, diba? So, pila man ang centroid ani, katunga ani. If we try to look at in the table, that is, ano to siya? W18 by 65. W18 by 65. Ang ihang depth is 8.4. I mean, 18.4, diba? Kani siya. W18 by 65 is 18.4 ang depth. So, katungaan na, katungaan ni plus this 3/8, diba? Or we can use this 18.38. Actually, pariharam na siya. Rounded lang ang, wala nakita. Rounded lang ang 18 and 3/8. So, to compute for the kuan is ano naman tong calculator. Right. To compute for the kuan is half of, that is 8. Ano naman to siya? 18 and 3/8. 3/8, no? Divided by 2. 9.1875, diba? Kani siya. Kani. That, muna siya ang, gikan sa kuan. Bati. Kana. Gikan ana, that is 9.18, diba? 1875 plus pagid ka og thickness nga 3/8 from the reference line. So, munang 9.5. In here, pila yung answer niya? 9.75. 9.75, no? Or, let me try 8.4. 8.4 man tong ganina, divided by 2. 18.4 ay. Sorry. 18.4. 0.4 divided by 2 equals, kana siya, no? Ang katunga, plus 3/8. Okay. Muning 9.7575, no? The distance is plus kani pagyod, no? Plus this thickness. Muna siya ang whole 9.75. 9.575. So, mana siya. Then, the reference, actually, this 8.893 is the centroid, is from the reference, from the top, to the, somewhere here, no? Dili ra kaabot sa 9. So, basin mga, ano na ikuikuan, oh? So, basin mga, diha ra siya tama, no? So, this is the 8 point, pila to? Centroid, 8.893. Okay. And with the location of the horizontal centroidal axis known, so natin centroidal axis, no? Horizontal centroidal, the moment of inertia with respect to this axis can be found by using the parallel axis theorem. So remember this formula, diba, in your statics, no? Rigid bodies. Now for all component, you have to where this I bar is the moment of inertia about the centroidal axis of the component area. Now each component area, then the area is area of the component, no? Then the I is the moment of inertia about an axis parallel to the centroidal axis of the component area, no? For the whole, no? Whole built up member. And D is the perpendicular distance between the two axes. So we have here the contributions of each component area are computed and summed to obtain the moment of inertia of the composite area. Okay, these computations are shown in table 4.3, which is expanded version. So we have here the table, no? Actually, gi-expand lang ni siya sa table previously. So you have the area, the A times the Y bar, times the moment of inertia of each component. So we have for the plate, is actually, this is, to get this one, this value, for the plate, this is BH cube over 12, diba? But your B is, with respect to X, 4, no? 4 times 4 inches. Now, 4 inches times 3 over 8 cube over 12. So, pila na siya. Hindi na ito mag-calculator na kuan kay murag. Okay. Na-erase na niya akong calculator sa kadugay. Divided by 12. So, you have 0. Na siya. That is the answer actually. 0.015758. Then, for the wide flange, the moment of inertia for the X, no? Along X, inyong tanawon diri sa table. Wide flange. So, you have, wala diri. So, meaning, possibly na diri, no? You have this 65, then the moment of inertia at x-axis is this 1070. No? Okay. 1070, so, mo ng 1070. Then the T, this is the distance, no? Between the centroid. So, centroid ani, distance sa whole centroid of the component. Like, for the plate, diba? To get this one, is the centroid, pila tong centroid ganina? 8.893 minus half of the thickness of the plate, diba? 3/8 divided by 2. So, pila man na siya, diba? That is the distance between centroid of the individual component to the whole component. Ng 8.7055 or 8.706. And for this wide flange is 8.893 minus the centroid is 9.575. Actually, the result is negative, but remember, the formula is d squared. So, ma-positive lagi hapon siya. Diba? So, never mind the negative value. 8.893 minus 9.575. 0.682 negative, or actually positive na siya because that is the difference in the distance between this individual centroid and the whole centroidal distance, no? Okay. For the vertical axis, now we have like the need not to compute for the vertical axis. So this is for along y, di ba? Along y actually is you have to get first the moment of inertia of the plate and the moment of inertia of the wide flange from the table along y. So the moment of inertia, this is for the plate, no? This is for the plate. This one is for the, sorry, this one is for the plate. And this one is wide flange, W shape, but this is from the table, no? Table AASC manual. So, kung tanaw nimo siya, the moment of inertia of the W18/65 is 54.8 in axis YY. So, munang plus 54.8. So, this is for the plate. So, munang bali, ang mahimo nimong base is the BH cube. Mahimo nimong base is the thickness na. And the width is nahimo na siyang height, no? Divided by 12. So, BH cube over 12 plus this moment of inertia along y-axis of the W18/65 from the table. Then, compare, no? This is the moment of inertia at x-axis, which is equal to 1,193 for the whole component. And this is the moment of inertia along y, or in the vertical axis. And since comparing the two moment of inertia, no, vertical axis is less than the horizontal axis, no? So the y-axis controls. Meaning, di ba, we have to remember in the KL over R, di ba? Critical siya kung dako kaayo ni siya nga value. So, kung dako kaayo ni siya nga value, meaning your radius of gyration is minimum. So, dapat your radius of gyration here is minimum. Di ba? So, para minimum ni siya, your moment of inertia should be the smaller one. Or minimum also. Di ba? So, this minimum radius of gyration is your Ry because the y-axis controls square root of the moment of inertia along y-axis divided by the area, the total area of the whole component. So, the moment of inertia is 56.8. So, the minimum radius of gyration is 1.661. So, that the critical slenderness ratio KL over R minimum is 15. This is given in the problem. The effective length times 12 to convert to, because this is 15 feet, to convert to inches, so times 12 divided by the radius of gyration. So the slenderness ratio is 108.4. Then from this one, you solve for the Euler's buckling stress, Fe, no? Yes, Fe. The Euler's buckling stress is this formula, diba? Pi squared E over KLR squared. So this slenderness ratio is the computed slenderness ratio, 108.4. Then this is the modulus of elasticity of the steel, 89,000 KSI. So the effective, the Euler's buckling stress is 24.36. Then, Kanisha, from this one, remember, we have to compute this one, diba? This relation, no? So that if we compare this one to our slenderness ratio, we will know what formula to use for the critical buckling stress, flexural buckling stress, no? So, compute this one, no? Also 4.71 square root of V over Fy. Then, Fy is also given the problem, 50 KSI. So, the result is 113. And compare this one to the computed, no? KL over R, slenderness ratio. This KL over R is less than the 4.71 square root of V over Fy. Meaning, you have to use the equation E-2. So, we already discussed this one, no? If this condition is met. So, you have to use this formula, 0.658 Fy over Fe to the power of Fy over Fe times Fy, no? So, the critical buckling stress, no, from this one is 21.18 Ks. So that from this critical buckling stress, the nominal strength is critical buckling stress times the gross area, which is the total, no, gross area, which is we computed as 20.60. So, the nominal strength is, this is kilopounds, no? Because this is force-man. So, 436.3 kilopounds. To compute for design strength from this one, for LRFD is just multiply this one with the resistance factor 0.9, diba? Remember this 0.9? Excuse me. And for ASD, from equation 4.7, the allowable stress is alright. If I try to solve this one, okay, using this critical buckling stress now for ASD and use this 0.6. I mean, we discussed this one already, no? In the previous discussion, no? We arrived this one, or this the basic, one of the basic relation, no? For AASD solution. The applied force is equal to 0.6 times the critical buckling stress, which is equal to 21.18 KSI. Yes, because wala may kaka-indicate sa problem nga dead load, live load. So, we automatically apply this critical buckling stress to ASD solution, no? 0.6 times 21.18 is equal to 12.71 KSI. So that from this one, allowable strength is this times the gross area, no? So ASD solution is equal to, for ASD solution, the allowable strength is 262 kilopounds. Therefore, the design compressive strength, this is for LRFD, no? Solution, and from from ASD solution, the allowable compressive strength is 262 kilopounds. So, dili pareha ang ilang answer na for LRFD and ASD solution. So meaning, this is the design compressive strength. Mas dako ang LRFD compared to ASD. So we can like maximize the design with using LRFD solution compared to allowable, no? Compressive strength. So allowable man siya. But of course, for both ASD and LRFD solution, dapat your applied or the loads, no, should not exceed these two solution result, this design compressive strength for LRFD and ASD, no, both design compressive strength and allowable compressive strength. So this table is the summary, no, for the design of members for compression and can be found in AISC chapter E. For example, you have this cross section, this one, then can be found in sections without slender elements, no, can be found in sections E3 and E4. So the limit states for this without slender elements for this cross section is FB and TB. This FB is flexural buckling and TB is the torsional buckling. Then if this cross section for with slender elements can be found in sections chapter E, the limit states is LB. You have the local buckling, LB, FB, flexural buckling, and torsional buckling. In this section, no, and another is this section. This is the built up sections, no, shapes. Right, and so on, so forth. Then the unsymmetrical shapes other than single angles can be found in E4. The limit state for without slender elements is FTB, flexural torsional buckling, and with slender elements LB and FTB, local buckling and flexural torsional buckling. This is the last slide. You solve the assignment. Okay, I'll post this one now again, as this I think kung ano lang ni siya sheet work, I mean sa laboratory na lang ni siya nga practice na exercise or sheet work. Okay, we're done with the compression, no, members and design compression members. We'll proceed next week after na midterm topic is beam and beam columns. So beam, sunod atong topic ani is beam. So I think this is all.